So today we're going to shift gears and talk about the second type of reaction called single replacement. Once again, we need our fabulous actors who helped us last time. Who were they? We need the two guys and the girl that falls in love. Natalie.
And not the other girl?
Not the other girl.
Okay.
Sorry. Put him down, please. Okay, so you were the one who fell in love with Natalie, right? Okay. Here's the situation. We thought that things were better. We thought that there was some energy, electricity in the air, and we thought that they had fallen in love. Apparently, Lenoir here has some self-esteem issues, and he was thinking, stop that.
Sorry.
He was thinking, she is too beautiful for me. There's no way. I thought she liked me, but there's no way that she can like me. I'm not good looking enough. I'm not smart enough. She's too much for me. I don't deserve her. So you put your head down in shame. Okay, so he's got these two markers, which represent two electrons. He has his full complement of electrons. We're going to find out later that metals have electrons in what we call the outer shell, and they desperately want to get rid of them. Metals, please, stop. Okay, metals want to get rid of their electrons. Actually, what we find out is that in order to go into the watery dance floor that we call an aqueous solution, metals have to give up their electrons in order to become positive ions. Only positive or negative ions can be on the dance floor. Only positive or negative ions can be on the dance floor. Okay? In order for these guys to go dancing, you had Ryan, who had full complement of electrons, and you had Natalie, who had a full complement of electrons. Okay? Unlike guys, girls, non-metals, want electrons. They want extra electrons. They want to become what kind of ions? Atomic. No. Negative ions or anions. Okay, so in order for them to go dancing, what had to happen between them? No sharing. Yes, who needs to give? Ryan needs to give, because Ryan is representing for us a metal. And metals want to give electrons away so they can become positive. This is their gang symbol. Okay, so they go around, hey, this is their gang symbol, positive. Okay, the anions are going around, hey, this is her gang symbol, hey, negative. Okay, because that's what she wants to do. So, let there be a transfer so you guys can go dancing. Here's your, okay, so she is now negative. What happened to her charge? She at one time had her full complement. Full complement of electrons means she has a charge of 0, no charge at all. But now she's -2. So what happened to her charge? It went down. We have a special name for this in chemistry. It's called reduction. So when your charge is reduced, we say that you were reduced. You underwent reduction. He reduced her by giving her his electrons. Okay? So she has been reduced. Now, I wish that I had a name that made just as much sense as reduction for what happened to Ryan, but I don't. Adduction. I know, it would make sense if it was increasification or adduction, but it's not. It's called oxidation. Now, why is it called oxidation? Because very early on, we realized that Ryan, metals, easily reacted with oxygen. So when a metal reacted with oxygen, we said that it was being oxidized. Now, once we began to understand the concept of electrons, we came to understand that Ryan, the metal, was giving his electrons. But by that time, it was already too late. We could have called it adduction, but it was too late. The name had stuck. Oxidation was the name. So even though it doesn't make any sense, even though it would be better to call it adduction, The fact is, it's called oxidation. So when your charge goes up, you are oxidized. When your charge goes down, you are reduced. Okay? Now, here's the problem. Mark wants to get on the dance floor. She's got her full, that's it. Girls want to be negative, she's negative, she's done. She's already been reduced. But here's a guy that is happy and he's lost his electrons. Okay? He can't lose any more. There's no more to lose. But can he gain more? It all depends. Look on the back of your periodic table. Now remember, your goal in life is to be positive. Are you positive now?
Yes.
Are you happy now?
No.
Yes, you are happy. That's your goal in life.
Okay.
So are you happy now?
A little bit. I'd be happier if I was more.
Okay. Mark, is he happy?
No.
No, he's zero. He wants to be positive. Okay, so let's go and ask Ryan nicely if he would be willing to take your electrons. Okay, Ryan, you will be unhappy.
Yes.
You will be unhappy. Guys, this is on the internet.
I love
Okay.
no better.
Okay, guys, please, you're hurting my metaphor. You're not qualified. Okay, so, give him back the electrons.
Oh.
Do you want those electrons?
No.
No, he does not want those electrons. Okay, so the question is, asking nicely did not work. Will force and violence work? Let's see. Go to the back of your periodic table and get on there on the lower left section. There's this chart called the activity series. That tells you that ranks guys and girls from top, which is the toughest, meanest, to bottom, which is the wimpiest. Okay. Mark is zinc. Ryan is silver. So, find zinc and find silver. Is zinc, Mark, man enough to force the electrons? Okay, so when you give him the electrons, what happens to him?
He goes to zero.
Give him the electrons.
Take it.
You don't have any choice. Take both.
But what vote?
Okay, he doesn't want it, but okay, you're sad. What happened to him? He went back down to zero. What happened to him? He was reduced. His charge went down. He now has his full complement. He's zero. He's going back to a solid form. And he is sad. He's very, very sad. Okay, so get off the dance floor. You don't deserve to be on the dance floor anymore. Marco Polo. He is now positive. His charge went up. What do we call?
Oxidation.
Oxidation. His charge went up, and now he can make that gang symbol, right? The gang symbol, the plus. He is positive, and now he can dance. Okay? Noah, get up here. So Noah is yet another medal. He is, we call him Golden Boy. Golden Boy. Okay, so Noah wants to get in on this action. He notices that he's lost his electrons, and he thinks, well, maybe I can bully him into taking my electrons. Is it going to work?
No.
Where is gold?
Gold is on the bottom.
Okay, so push him away. You remain king of the hill, of the pool at least.
Wait,
All right.
that means I'm positive now.
No, you're still there. So you and he join.
But I
So
beat
when
him
it's
up.
below, when the metal is below the other metal that's dancing, no reaction. Nothing can happen.
Wait. What about the ones that are in line?
In line.
Yeah, like get rid of things.
No. What? No. Girls and guys. Girls and guys. This can happen. You want to try it for the girls? Yeah. Get up here, Morgan and Molly. And who are you going to fight over? Let's fight over Noah. Okay, Ryan, thanks. Let's fight over Noah. Okay, so let's try this again. All right, thanks, Natalie. take these and go stand over there. These are your natural electrons. Okay, so everyone is 0. In order for them to dance, what has to happen? This is the metal, this is the non-metal. What has to happen?
He has to give her.
That's right. You have to give. Okay, so what happens to him? When he is positive, he is what? Oxidized. Okay, is she happy now?
Yes.
Yes, because she was
Reduced.
reduced. Girls want to be reduced. Non-metals want to be reduced. Okay, and now her friend is jealous too. Look jealous. Ooh. Look at those electrons. She's got 2 extra electrons, and you don't have any extra electrons. She is flooring. She's roaming. Let's see what happens. Go be a woman about this and take those electrons. Can she?
Yes.
Take all of them.
Yes, she can.
All of them.
No, you can't take all of them. Leave her some. Okay, so what happened to Morgan's charge? It was -2. Now it's what?
0.
Now she's gone back to normal, 0.
No.
She was 0 and now is.
-2.
So what happened to her? She was
Reduced.
reduced. What happened to her?
Oxidized.
Okay, so you understand they're not in line. It's 2 different situations. So girls can fight over guys and guys can fight over girls. All right, thanks.
Woo!
All right. Single replacement, general formula. Let's see. We had Ryan and Natalie, and Mark is the wallflower, right? And then the reaction occurs, and now Mark is dancing with Natalie, and Ryan is the wallflower. The metaphor we use, somebody that stands on the side of the dance floor and doesn't dance. A wallflower. Cutting in, right? Does that make sense? Cutting in. Now in the real life, they would tap each other on the shoulder, right? And look at the girl, and the girl would either nod or say, no, please. Yes, Ryan.
Where's the thing on the back?
The activity series. Okay, so here is some potassium. It's off the dance floor. Here is some hydrogen ions. It's acting kind of like a metal. Okay, so it's positive gain. Is potassium able to replace hydrogen? Is potassium higher on the chart? Okay, so what you're seeing here is all the hydrogen being produced. Actually, the hydrogen, as it's being produced, it encounters the oxygen in the air and it's catching on fire. So alkali metals will do that. Zinc. Can zinc replace hydrogen? Look at it.
Yes.
Okay, so what you're seeing here, these bubbles, those are hydrogen bubbles as they're being reduced back to their natural state.
Would it also
H2. What?
would the hydrogen still catch on fire when it got out?
Yeah, when it gets out, it could potentially catch on fire. All right, these are called redox reactions because it's reduction oxidation. Reduction oxidation.
But what's up with those words? You know what reduction is, making less of something, and then oxidation maybe has something to do with oxygen, well, sometimes, but not always. These are actually super terrible choices for what is actually happening in redox reactions, but we are stuck with them. Reduction is when a substance gains electrons. Yes, it gains, which is the opposite of what the word reduce means. Fantastic. And yes, sometimes I want to punish the people who named these things so inaccurately, but they didn't know any better and they're all dead, so we can't do anything about it. Proto-chemists would make pure metals by heating or smelting their ores. And they noticed during the smelting that these substances would become lighter, so I guess it's not crazy that they decided to say that these substances were being reduced. Our old French friend Antoine Lavoisier figured out that this was because oxygen gas was actually leaving the the compound, making it lighter. What he didn't know was the actual chemistry involved. Oxygen is, unsurprisingly, the quintessential oxidizer. It pulls electrons off of one molecule to make itself more stable. But if you heat it up enough, it gets all energetic. Today, we understand that oxidation and reduction are all about electron transfer. So you might think that we'd rename them, and some chemists have tried producing terms like electronation and de-electronation. But once a set of terms is decided upon and used for a while, it's pretty difficult to uncreate it. So we're stuck. To keep these seemingly nonsensical names straight, I rely on the phrase oil rig. Oxidation is loss of electrons, reduction is gain of electrons. We just gotta know this stuff, because it's everywhere. When your cells convert sugar into energy so you can move and breathe and think, that's redox. When plants photosynthesize sunlight into food, that's redox. The battery powering your laptop? Redox. Fire? Also redox. Since electron swapping is the name of the game here, when you study redox reactions, it's important, critical, absolutely essential to keep track of the electrons. Think of them as dollars or pesos or pounds or euros. In any transaction, one person is going to gain them and the other is going to lose them. And to stay on top of things, you have to keep tabs on who's ahead and who's behind. Start out with a simple example, a chemical reaction that I believe has saved more lives than any other in the history of chemistry, created by a war criminal to blow people up during World War I, the Haber process. The Haber process removes the ultra-stable elemental nitrogen from the air and combines it with hydrogen to form NH3, ammonia for use in bombs and also in fertilizer, increasing the carrying capacity of the Earth by billions. Nitrogen in the air exists as elemental diatomic nitrogen, and hydrogen likewise is also diatomic H2. So we know that starting out, all of the atoms have an oxidation state of 0. The product of the reaction, ammonia, is a neutral compound with 1 nitrogen and 3 hydrogens. The hydrogens each have an oxidation state of +1, remember the rules, so nitrogen must have an oxidation state of -3. Nitrogen thus gained electrons, its oxidation state went down, and so it was reduced. So at least when talking about what oxidation states are doing, the word reduced makes sense. Hydrogen lost electrons, the oxidation state went up, and it was oxidized. Now,
all right, so let's look at what's happening here. First thing I need to get across to you, and this won't be the first, this will be the first, but it won't be the last time I tell you this. There are 2 types of reactions. Only 2. Double replacement that we have already dealt with, and no. Reduction oxidation. Reduction oxidation. That's it. The other 4 types, which I've already talked about single replacement, the other 3 types of reactions are all redox reactions. Redox reactions is like half of chemistry. So that's why we're going to cover it today. We're going to hit it hard, and we will deal with it all year long. Okay? So, let's look at an example here. Magnesium. Any element that is in its natural state has a charge of 0. Hydrogen is +1, becomes magnesium +2, and hydrogen, is it in its natural state? It has a charge of 0. All right, so let's look at what happens to magnesium. Magnesium's charge goes up. What is the fancy word that we use for upsizing? Oxidation. Very good. What happens to hydrogen? It goes down. It is reduced. Before we go on, let's go through. I know that a lot of times you're used to number lines being horizontal. Think of the number line here as being vertical, where the middle is 0. Higher than 0 is, higher than +1 is, lower than 0 is, and lower than -1 is. So hydrogen is going from +1 to 0. Magnesium is going from 0 up to +2. So, magnesium becomes more positive by losing things. I know that's confusing. You would think that losing things would mean that you're being reduced, but no. Okay? Not if you're losing bad things, like maybe herpes. If you lose herpes, that's a good thing, isn't it? Just because you losing things does not mean it's a bad thing. So if you lose something really, really nasty like herpes, then it's a good thing. You're becoming more positive. If you gain herpes, that's a bad thing.
You know you're filming this, right?
It's okay. I mean, herpes is a sexually transmitted disease. It's something that you don't want. I'm not encouraging people to get herpes. I am actually putting it in a negative light. I have no shame in showing and talking about herpes in a negative light. You don't want it. Okay? So, magnesium is becoming more positive because it's losing two very negative things. Okay? So when you lose negative things, you become more positive, right? That is called oxidation. Hydrogen is gaining the negative things. So its charge is going down. It's a bummer. It got herpes. So it's not happy. So this is called reduction. Reduction in happiness occurs when you get herpes, right? All right, you get herpes, you are reduced in your happiness. Whatever it takes for you to remember this kind of contradictory vocabulary. I know, I'm sorry. What is oxidation? Early chemists noticed that most compounds reacted with oxygen. Later, they realized that what was really happening was that the metals were giving up electrons to the oxygen. Then they realized that it was more than just oxygen that could do this, but it was too late. Too late. The name had stuck. So we are stuck. Some scientists have tried to come up with the word adduction.
Why can't we?
No one uses it. Oxidation. So when you lose electrons, you are said to be oxidized. Here's another way of remembering it. Oil rig. Oxidation is losing. Losing what? Electrons. Reduction is gaining. Gaining what? Electrons. So if you remember oil rig, that might help you, Morgan. Oil rig. Oxidation is losing electrons. Reduction is gaining electrons. Reduction. Your charge goes down. You become less happy because you have gained electrons. You have gained electrons. All right, step number 1. Let's see if you can even recognize oxidation and reduction. Grant, look at this first one. Any element by itself has a charge of 0 to -2. Oxidation or reduction? Oxidation is when you go up in charge by losing negative things. Reduction is when you go down in charge by gaining negative things. Reduction. Noah, +3 to +2. Is that going up or down? And it's reduction. Phoebe, any element by itself has a charge of 2 + 2.
Is oxidation.
Because the charge is going up. Aluminum, +3. Morgan, aluminum in its natural state has a charge of?
Hold on. Wait, we got this.
No, you don't.
Yes, I do.
No, really, you don't.
+3.
No, you don't.
Okay, 0.
0. I told you didn't. When you make a move for the periodic table and the answer is 0, that's not a good sign. All right, what?
What is that +3?
It should be up here, +3. Okay, +3 down to 0. It's been what? reduction. Bromine, -1. And Ruthie, any element by itself has a charge of?
0.
So what is going on?
-1.
-1 to 0 is?
It's increasing, so it's oxidation.
Right. It would be best if it was called increasification, right? But it's not. It's called oxidation. All right, before we go there, let's go back here. Just 1 second, just to make this clear. When you are being oxidized, electrons are being produced. So electrons are released. It's part of the product. So whenever you see electrons in the product side, that is a good indication that it is oxidation. When electrons are being absorbed, like here, that is reduction. So oxidation is losing electrons. Reduction is gaining electrons. All right. Warning, warning, warning. Like double replacement reactions, these things are going to take place in watery solutions. You should expect spectator ions. Unlike double replacement, where you have 2 spectator ions in single replacement reaction, you should only expect 1 spectator ion. The solubility chart, the solubility song, solubility rules was the key to doing double replacement right. For these, the key to doing these right will be the activity series, because whether something occurs or not depends on where it's at on the activity series. Be careful with diatomics. Remember that there are 7 elements that in their natural form are a twosome. And finally, please write correct chemical formulas. Balance the equation. All right. Behold, single replacement reactions. Zinc and sulfuric acid. Okay, you're going to find some similarities of double replacement. They're going to be easier. You're going to say, well, why didn't you teach this one first? Because you wouldn't find these things to be easy if I had taught it first. They're easy because now you've gotten used to the way we do things with double replacement reaction. Zinc. What is the natural state of zinc? 0. What is its phase? No. Solid. All metals are solid except for one. Which one's that? Mercury. Sulfuric acid. All acids are aqueous. All acids are aqueous. All right, before we get started, we need to know whether this is even going to work. What kind of cutting in situation is this? Because this is the 21st century. We could have a girl trying to cut in on a couple, or we can have a guy trying to cut in on a couple. Now, one thing you must not forget is that there is no homosexuality in chemistry. Not because of sexuality reasons, but because of charges. 2 positive things cannot come together. 2 negative things cannot come together. So you need to make sure you keep the genders correct. Metals, we think of them as being guys. Hydrogen is a non-metal that looks like a guy. Yeah, so treat her, him like a guy. And here is a group that is non-metals. Now notice over here I did not circle H. Okay, I didn't circle 2. Why did I circle the 2? Isn't H a brother? Yes, H is a brother Huncliffe, but not when it's part of a compound. The reason why it's a 2 is because it needs to be a 2 in order to balance with the sulfate. That's it. So you don't take it to the other side, not necessarily. You may need to, but you don't take it initially. Okay, so this is boy, boy, girl. Okay, so this is Morgan's dream come true. Two guys fighting over her. Okay? Oh, judging from that cough, there seems to be history repeating itself, right? All right, Morgan, look on your little black book activity series. Are you willing? Is zinc man enough to give hydrogen its electrons? Is zinc higher up on the chart? Hydrogen. Yes! Well, boo, because now instead of putting down no reaction, we actually have to go through with this reaction. Okay, so on the other side, zinc is now with Morgan. Morgan is -2. Everyone knows she's -2. Zinc is +2 when it's on the dance floor, so that's correct. I am scratching them out. And
I thought guys like to be negative.
no, guys want to be positive, girls want to be negative.
Right. Just like in real life. Girls like to be negative.
All right,
I'm just right.
Mark, be quiet. All right, now hydrogen is kicked out of the dance floor to its natural state. What is the natural state of hydrogen? It is a brother Huncliffe. So its natural state is H2, and what is its phase?
It's a gas.
It's a gas. Okay, let's see. Sulfates. Sulfates are soluble, it said, except with barium, strontium, and lead-2.
Wait, I thought we could not use the song for this.
No, I did not say that you could not. I said that activity series was as important as the solubility song was in double replacement. So all sulfates are aqueous except for barium, strontium, and lead-2. All right, is it balanced?
Hold on.
It's ugly, but it's balanced. Okay. Yes.
So, wait. Okay, I think I did it.
All right. Anything that is solid, liquid, or gas, leave alone. Anything that's aqueous, just like we did with double replacement, break it down into its ion form. So zinc stays solid. All right, H2, does it come down as H2 or does it come down as 2H plus?
2H.
Yes. Only these numbers that are wrapped around polyatomic ions come down as is. And hydrogen comes down just as it is. That is the total ionic equation.
Is that all you do?
No. At this point, in double replacement, we eliminated 2 spectator ions. And we knew that we had done it right if there were 2 on either side that were exactly the same. There's only one that you know you've done this right if there's 1 ion on both sides. It's exactly the same. And that ion is, Morgan?
What? 2 ions that are the same. Hold on.
Zero.
We're getting there.
Zinc goes from 0 to +2. That's a
not the
change.
same.
+1 to 0.
Yeah, okay.
-2 to -2.
Yeah, so SO4 and SO4.
All right. Bring down everything else.
So that's all you do?
Almost.
Almost? This is harder than double replacement.
Fine. It's harder.
Brenton, please be quiet.
Does something have to go there?
Now, this is where we would have ended it with double replacement, right? Okay, you need to add one little piece of information. I want to know who was reduced and who was oxidized. So, let's look. Zinc is going from 0 to +2. What happened to it? Therefore, what happened to hydrogen since it's going from +1 to 0? Okay, that's not going to be good enough for me. I'm going to use Noah as an example. So, I am higher up on the chart than Noah, so I come over and I say, Noah, you little wuss, take my 2 electrons. So Noah has no other choice but to take my 2 electrons. Now I am happy because gang symbol plus, right? I am now a positive gang member. All right? I am now positive. What happened to me now that I'm positive? I was oxidized. What happened to him? He's sad. He went down. No, I just gave you 2 heads. Okay, so what happened to him? He was reduced. Who reduced him?
You.
I did, making me the reducing agent. I was oxidized, but I reduced him. I am the reducing agent. Because I was oxidized, who oxidized me?
Noah.
Noah did. What kind of agent is he?
The oxidizing.
Did you notice a relationship? He was reduced. He is my oxidizing agent. I was oxidized. I am his reducing agent. So, best way to remember this is opposite agent. Opposite agent. So if you are oxidized, you are the... If you were reduced, you are the... So, those are the 2 little pieces of information that must be added to all of these. Yes?
For the elements that are in their natural state, do you have to say that they have
No. But oftentimes it won't hurt to have it there, and it helps you see who's being oxidized and who's being reduced. No. All right. Let me show you zinc being oxidized and hydrogen being reduced. To classical music. What are the bubbles? Hydrogen gas.
That reaction, is that in there actually?
It's going to heat up. That's a good question. Eventually, what's going to happen to these pieces of zinc? Eventually, what happens to the pieces of zinc? They go away. They become zinc ions. You won't see them anymore. And all the gases will disappear. All right? Second example. With this one, I'm just going to ask you rhetorical questions in order to help prompt you. All right? Rhetorical questions or rhetorical statements. Anything in its natural state has a charge of rhetorical questions. Aqueous silver nitrate. Silver has a charge of. Nitrate has a charge of. Aqueous. Thank you. I've done this a time or 2.
Well, you almost forgot.
You cross out CUO.
You don't have to. That doesn't hurt anything.
Okay.
All right. Rhetorical question. Is copper man enough to shove electrons into silver?
Yes.
Rhetorical questions.
I answer myself and sometimes too.
All right, listen. Listen to my question. Copper, when it becomes an ion, can either be +2 or +1. I wonder which one it is. The answer? I'm going to answer this question. The rule is always choose the higher of the two charges. So if it's either iron 2 or iron 3, choose iron 3. If it's copper 1 or copper 2, choose copper 2.
Does it always work out that way? Or is it
No, but for now, just assume it does.
So then why did that one?
I went to the higher one, which is 2.
No, but like on that side, it's CO, it's CO.
Yes, it goes to the higher of the two charges.
Oh, okay.
Copper can either go to copper 1 or copper 2.
Okay.
Choose copper 2. Is silver one of the brother Huncliffes? These people don't know what rhetorical questions are.
Wait.
All metals are solid except for... Is it balanced?
Hold on.
No.
Mr. Miranda?
Yes.
Please use the restroom, sir.
Yes.
Thank you, sir.
Anything that's aqueous needs to be broken down. Anything that's liquid or solid or gas needs to be left alone.
When you're writing the charge, you're going to add your charge. You have to put the 0 to the...
No, you don't have to, but it helps. So if I've done this right, there should be one ion that looks exactly the same on the left and the right. And that ion is? Nope. They still don't know what rhetorical is.
Oh, that was a Wait, I have a question.
Go, Phoebe.
How is the AG balanced on both sides? Because one's too.
Very good. Yes. That was a mistake. Good job, Phoebe, for catching that. Awesome. All right. Then you write down what's left over. Bless you. Somebody must have gone up. Somebody must have gone down. I like to focus on who's gone down. Who's gone down rhetorically? Oh, you finally got it. Making it the... most of you got it. Who's gone up? Making it the... Finally, you've understood what rhetorical means. Any questions on this one? Third, This one's really neat. Watch this. They're going to put a piece of copper in silver nitrate. Silver nitrate is clear. You won't be able to see anything. Copper is coppery looking. So what happens when copper comes in contact with silver nitrate? Aha! Almost instantaneously, guess what that silvery looking material on the copper is?
Silver.
Silver. Okay, over time what's going to happen is the weight of the silver will cause it to come down. Watch.
Oh, that looks cool.
Now, what's happening to the color of the liquid?
It's turning green.
Bluish green is indicative of copper ions. Look. So it creates copper ions, which makes a blue liquid, and silver, which makes that silvery material. So that down there is silver metal. And the blue liquid is copper ions. Yes, but silver nitrate is more expensive than silver.
Oh.
So you're not going to turn a profit. All right, here is
Is that
Grant's.
basically what we did with the zinc thing? No.
Here's Grant's dream come true. Is chlorine a diatomic? Yes, it is. Gas is bubbled through a sodium bromide solution. Sodium is +1, bromide. Why is it Grant's dream come true?
Because it makes salt.
In the last two reactions, you had two metals fighting over a girl. What is chlorine? A girl. Sodium. So Grant is sodium, and chlorine is trying to cut in on this dance. All right, look on your little black book, Grant. Is chlorine an upgrade or a downgrade from what you've got? Look on the girl's side. There's a guy's side, which is the left. The girl's side is on the right. What? Upgrade! So you're going to allow it to happen. Not that you really have a choice. So chlorine comes around, and it's the opposite. She takes away 2 electrons and absorbs them. So now she is negative, and Grant is still positive. So now they form a couple. And bromine's been kicked out into the cold. Is bromine one of the Brother Huncliffes?
Yeah.
That's where we get brother from in Brother Huncliffes. And does anyone remember what the phase on bromine is? Bromine and mercury are your only liquids. All right, is it balanced?
No.
Is that mackerel that you make, is that edible?
Salt water. Most people don't like to drink salt water.
But it wouldn't make salt water, it would make salt bromide.
No, it's making salt water and bromine, which is poisonous. All right. So, is it balanced? Now is it balanced?
Yes.
No.
No.
Now is it balanced? Anything that's gas, liquid, or solid remains the same. Anything that's aqueous gets broken down.
Well, what I'm saying is, if you separate them, could you use that salt?
It's not going to form salt. It'll be dissolved salt. It'll form salt water.
Yeah, but you could like boil it off.
Okay, yes, it would be possible. If we've done this right, how many ions should disappear? Goodbye, Grant. He does nothing. The fight is between the two girls. He just sits there and watches with a smile on his face.
Wait, what did you say would make it a no reaction again?
If this was iodine, iodine is below bromine on the activity series.
Okay.
All right, so who's going down in charge? Nope, not rhetorical anymore.
The
Cl2. Who's going up in charge? So if that's oxidized, then what kind of agent is it? If this one's reduced, what kind of agent? Done. One more. Before we do that, let's see it. They're going to actually give you a liquid that contains chlorine gas in it. So watch what happens. As they pour in the chlorine gas, look at the bromine liquid appearing. That's bromine liquid. That's bromine liquid. And down here is the dissolved chlorine and sodium ions. All right, Marieli, you're back in charge here. Silver wants you. Bad. Zinc has you. Silver tries to cut in. Are you going to let it? Consult your little black book. That is so superficial. You know, guys have feelings. She's got these guys all rated. Are you going to let it happen? Silver's below. So you'd be going with an uglier guy. No, yeah, like no reaction. Yeah. No reaction. You know what? That ugly, nerdy guy is going to grow up to probably be a multi-millionaire in the computer industry. And that good-looking guy that you decided to stick with, well, he turns into an alcoholic bum. There. All right. That is single replacement reactions.